Okay, these videos for section 10.1 are getting kind of long, but there's one more kind of problem that I need you to understand from section 10.1, and that's a problem where sometimes they ask you to use the margin of error to somehow solve for the sample size. Let me remind you that in general, our formula for confidence intervals is statistic plus or minus margin of error. So again, for the specific one we're talking about, the margin of error is everything after the plus or minus in the formula. So the margin of error that we're talking about is this quantity z star sigma over root n. This is the margin of error, okay, which is going to come up in the future problem. So here's a quick example. So let's say we know sigma 7. This relates to the commute example we just did. You want a 99% confidence interval to be accurate within plus or minus 1. So what they're saying is you want your margin of error to be 1. How many people must be in your sample? Okay, so again, the margin of error is z star sigma over root n. When they say you want to be accurate within plus or minus 1, they're saying, hey, you want your margin of error to be 1. So here's our margin of error formula. We just set up an equation. 1 equals z star sigma over root n. Okay? We know sigma 7, so notice I replaced the sigma with 7. We can calculate the z star value. It says we want to be 99% confident, so we'll get some practice with this, but actually you can do inverse norm of 0.995. You get this number, and then, hey, look, you just have to solve for n, which I just cranked out the algebra. I multiplied and divided. You get n is about 326.11. This is a number of people, okay? Well, you can't have 325.11 in your sample. So you actually always round up, because if it was actually 325, this number would be slightly less than 1. We need to be at least 1 or more, so you always round up when you're doing these problems. Okay? 326 people would be the answer. How many people would be in your sample? So there's some good thinking we can do about margin of error, right? So this is our formula for margin of error, right? Let's say you want a narrower confidence interval. So that would mean you want your margin of error to be smaller, which is a really important thing. If you want to be as accurate as possible, I'm not crazy about the term accurate, but let's say you want the smallest confidence interval you can, the narrowest confidence interval you can, you want this number to be as small as possible. Well, what are some things you can do to make your confidence interval narrower? Well, couldn't you make n bigger? Because if n is bigger, this whole quantity becomes smaller, because n's on the bottom. You could also be less confident, maybe change from a 99% interval to a 90% interval. Wouldn't that make the z star value smaller if you were less confident? And that would make all of this decrease. Okay? You could also, in some situations, you can make sigma lower, though usually sigma is a parameter for the population. So this one, almost never do you actually are able to control your population and make sigma lower. You can't just suddenly say the sigma for the population is lower. So these are really the most two common ways you can make a narrower confidence interval. Now think about, what's the problem with making n bigger? Well, it's logistically harder. You have to ask more people, right? So very often, there's budget restraints and things like that. And just the last thing in section 10.1, our book ends with what they call some words of wisdom about confidence intervals. Just remember, you always have to have a simple random sample. It's not like, this math gets pretty complicated or the calculations get really complicated, but it's not like suddenly you can take a crummy sample that's biased in some way and let the math support that. If the data you collect from your sample is bad, then basically any kind of calculations you do on that are meaningless. This is why we spent so much time back in Chapter 5 talking about sampling design. You must do a good sample. A simple random sample is not biased, otherwise any calculations we do by now are totally meaningless. You really must have good non-biased data. There are other kinds of sampling designs. Remember we talked about the stratified sample, cluster sample. Turns out there are other different crazy formulas that relate to those different sampling designs way beyond the scope of AP statistics. And so the only sampling design we're really going to talk about now is a simple random sample. If you got your PhD in statistics, your teachers might teach you other formulas that might relate to a cluster sample or those kind of samples, but we're not going to do any of that. From now on, simple random sample is the way to go. And remember, your confidence interval reflects only random sampling errors, this idea of kind of just random chance, right? You are 95% confident that something's between something and something, but there's a 5% chance it could have just been the sample you took was really, really unusual and you're outside of that range. It does not, there's a chance that your confidence interval, if you're doing a 99% confidence interval and you do 100 of them, one of them will actually probably on average not contain the actual value from you, and there's nothing you can really do to stop that. This idea of random sampling errors, it's all based on the idea of, when you take a sample, it could be anything. We know it follows the normal distribution of the sampling distribution, but there's a chance that a confidence interval could actually be incorrect in the sense that mu could not be in that range. It's not like you did anything wrong. If mu is not actually in your confidence interval, you still could have done everything right, and just by random chance, you had a sample that was kind of freakishly unlucky. And with really those words of wisdom, that wraps up section 10.1.